we're going to talk about electron configuration. So, as we saw with things like sodium, so sodium has 11 electrons. If we wanted to depict that, we have to fill the 1s, the 2s, the 2p, the 3s, and we have to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have to draw this rather large, cumbersome drawing filled with arrows and lines. And while it does represent how the electrons start filling the lowest energy orbital first, and then as that orbital fills up, they go to the next higher and the next higher, it is kind of large and messy. We need a faster way to write this. And so there is electron configuration. So if I want to talk about sodium, what I can tell you is that in the 1s orbital, there are 2 of them. And so what we've done is instead of drawing it and showing 2 half arrows, I just said, hey, in the 1s, and then in the superscript, I say how many electrons are in there. If I want to talk about the 2s, well, there's 2 electrons. If I want to talk about the 2p, there's 6 total electrons. Now, we don't have to tell you that there's 2 in each orbital because the orbitals always feel the same. They start spread out. So if I have 3p orbitals, they will start spreading. So if I had 3 in the p's, they'd look like this. If I had 4, they'd look like that. If I had 5, they'd look like that. And 6 has them full. So we can just tell you there's 6 in there, or 4, or 3, or whatever number there is, and we'd be able to figure out how they were spread out. And then finally, the last one, in the 3s orbital, there is a single electron, so it's 3s1. And so in this very quick fashion, I can show you where all the orbitals are, or all the electrons in the orbitals are, without having to draw the complex image. If I want to do it for an ion, sodium plus, we always lose electrons from your highest orbital first. So we're going to lose electrons from there. All that's going to be left is the 1s2, 2s2, 2p6, which is what we would have if we fill our 1s orbital, our 2s orbital, our 2p's, and then our 3s. If we only have 10 electrons, because we're sodium plus, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We will only end up with 2 in the s orbital, in the 1s, 2 in the 2s, and 6 in our 2p's. So electron configurations is a very quick way to show where all those electrons are without having to draw the rather large drawings. What we tend to find is if we look at things like oxygen, fluorine, and neon, if you actually write them out, we'll find that oxygen has 1s2, 2s2, 2p4. Fluorine, the next one line, has 1s2, 2s2, 2p5, and neon had 1s2, 2s2, 2p6. As we make their standard ions, well, neon doesn't change. It doesn't become plus or minus charged. It's a noble gas. It's neutral. Fluorine becomes F minus, and oxygen becomes F2 minus. So neon still has 1s2, 2s2, 2p6. Nothing changed between the 2 runs. Fluorine has 1 more electron. Goes in the highest energy orbital, so 1s2, 2s2, 2p6. And oxygen has 2 extras. So 1s2, 2s2, and instead of 2p4, it's now 2 more. 2p6. In fact, what we find is that when you have your standard ions, the ones we think are what we expect that atom to have if it's an anion, or if we never find it as an anion, or if we find it as a cation, what we'll find is that they always end up having the same electron configuration as the noble gas at the end of its row. So the second row of the periodic table, we've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And what we find is that fluorine becomes fluoride, and we have the exact same electron configuration as the noble gas. Oxygen becomes oxide, and we have exactly the same electron configuration as the noble gas. Again, this is because if your highest shell, so remember your number, these are the shells, there's a 1 shell, there's a 2 shell. If you have more electrons, you get into the 3 shell and maybe the 4 or even 5 shell. Well, if your highest shell, if you have filled your S and P's, you're very stable. And so noble gases do that by default. Fluorines need 1 more to become that way, so they normally are fluorides. Oxygens need 2 more to become that way, so they normally pick up 2 electrons to become oxides. And so electron configurations provides a faster way for us to show where all the electrons have gone, and it lets us see that, well, why are our ions what we normally find them as? Because that's when their configuration matches that of a noble gas. That's when their configuration is the most stable. All right, well, that concludes our electron orbitals and configurations discussions.